discussion a few workshops ago was the rather dire representation of women in computational astrophysics, which is a problem we would like to solve. And one of the ways we're solving is by awarding a prize talk to early career researchers. And it's my great pleasure to introduce Claudia as giving this year's Minuta Computational Astrophysics Prize Talk on simulating protoplanetary disks, protoplanets, and beyond.
So hello everyone, I am Claudia Toci. Currently I'm an ISO fellow, which means that apart from me killing myself, that I've been capable to convince people that are observers that we as computational astronomers sometimes are useful because we can help them and support them in understanding what we are observing currently. These days we already have seen a lot of application of observations. For example, the last one was rainfall or eccentricity in cavities, or also yesterday on self-gravity. Most important results for this workshop is that I made my first phantom logo. This is the Phantom of the Opera, and there are 3 versions of this. It's handmade, so this is this. There is a Super Mario reference, and there is also the Phantom reference into the Phantom of the Opera. So yes, that's it. So before talking about science, I think, especially for people that are younger than me in career, so I'm long-time collaborators. That means that basically I started my postdocs working with Phantom. I did my PhD in molecular clouds, MHD, equilibrium and collapses of prestellar cores, so not directly on protoplanetary disks. And I started to use Phantom only in 2018 when I joined Milano University to work on disks. And before joining basically the Phantom collaboration, I was working alone. And I want to tell people how lucky we are that we have a community. So this is them. This is the guy that is developing the code together with Beck there and Terence there. But all of us are contributing. And it's very important because all those points are basically made by us. And specifically, you meet with people that are doing what you are doing, but in a different way. So you learn a lot of things you can do, you can apply to what you are already doing. You learn basically that even your stupid mistakes sometimes are useful. For example, yesterday I told Beck that I inverted the dust sizes, and Phantom is fine, but for example, MC4 is not. Technically, when you are in a collaboration that is a numerical collaboration, you should also contribute to the code with your pushing and pulling. I am very bad at this because basically what I do is send my students to push on what we are working on. That means that's no pull request from me. I have to do one. And again, it's very important that we can learn from the mistake that we do together, and we can improve the quality of our simulations and also the reliability of our community with respect to the other communities, and how people see us, like as people that are reliable in using computational codes. And most importantly, you can have fancy images. I'm very bad at this, but I've seen some cool images shown in these few days. So as Dan already said, I started in basically working on disks, working with Phantom. And for me, it's been a very important milestone for my career because I basically learned everything I know about protoplanetary disks working with Phantom. And many works involved the young students that now are also postdocs, or they left science for academia, but they left the background of this. And most importantly, you also learn that sometimes what you do is, let me say, less wrong than some other times. So we have 40 minutes, 30 plus 10. Some introductions just for show fancy pictures, but then I want to show what I did with Phantom. I won't have time to show what I am doing with Phantom, so next Phantom workshop. I will show simply what I am pretty sure I understood, more or less. So those are the exoplanets we are detecting now. This is a mass versus basically distance from the star plot. Those are our ones. Those are the ones we are detecting now. Where are the planets? This is the leitmotif of this talk. So we see the planets when they are already formed. And by the way, I want to let you think about how difficult it is to see a planet. It's a dot on a black sky. So we are capable to see dots on a black sky, and we are not capable to see those dots where we know they are. And I think the reason is because they are dots, they are emitting, or reflecting or emitting according to the temperature, but they're embedded in other lights, like the emission of the disk. And this is what makes us very, very difficult to detect exoplanets with respect to just seeing a dot on, for example, also all of the shadow or the effect of this dot on the emission of the star. Some values that I found interesting yesterday. So we have a lot of single planets, but we have also a lot of multiple planetary systems. We want to form also these multiple planetary systems, which means that in our protoplanetary disks, that could be more than one planet embedded, up to 8. That complicates a lot our models, because the degeneracy of detecting a number of points, you don't know how many they are, in a thing that is emitting light is very, very difficult. And another thing that I really like is that basically you can select whatever planet at whatever distance, and they can have whatever eccentricity or inclination or orbit on the star or around your favorite star. So basically we have to use fantasy because it's very, very wide. The parameter space is very, very wide, and it's very, very difficult, to be sure of what we are doing. Another topic that I started to work specifically here in Grenoble with Nico, Francois, Gaspard Duchesne, and Antoine is basically the fact that there could be more than one star also together with more than one planet in protoplanetary disks. So this is a plot that I found here in this very nice exoplanet.eu website, and this is basically the distribution of binary planets, circumstellar planet, S-type planet, the distance with respect to the own star, and this is the distribution of the binary. They're both normalized. There are some issues on, we don't know if we don't see those planets because they're harder to see, or there is some, formation issue. But, we start to detect that we have 730 S-type planets around the binaries. So, it's considerable. And we also start to have some circumbinary planet 31. So basically, again, a huge variety of exoplanetary system to explain. And as I told you, and as you may probably know, we believe that they are forming and evolving inside protoplanetary disks, material surrounding young stars. What I like of protoplanetary disks is that we see something. If for people that are working in star formation, see something in dark molecular clouds, it's hard. While here we have very bright emission. So we see substructures in all basically the disks that are large enough to be detectable with our current facilities. And we see those substructures with basically all the tracers you may use, which means that those substructures are kind of physical. So they are, physical holes carved. Maybe not all of them. There could be some shadow. There could be narrow shadow. There could be broad shadow. There could be, some chemical dust properties that is changing in different location of the disk. But at least some of them are physical holes, and we need to understand why we have them. This is basically what I do now. So because it's so difficult to constrain at least, a property of what we want to test, we really need to rely with, to work with our colleagues that are doing observations. And if you want to work with someone that is doing observation, you really want to, offer them more than one observable, because you want to be at least capable to offer a way to break partially the degeneracy and, have some prediction to test. And specifically what we can do in protoplanetary disk is change the tracer. So once we have our model, and Phantom is very nice with this because it gives you the physical distribution in the three-dimensional space, we can use different tracers and different telescopes to probe different layers of the disk and find some properties of those disks. For example, we can probe large dust using ALMA, where large for us is millimetric dust. We can probe molecular line emission with ALMA, that is probing the upper layers according to the molecules you're using. But we can also probe the upper layers, small dust scattered on the very upper layers with, for example, VLT. And one thing that I always tell to people, and people know but tend to not remember, is that the same disk can appear very different using these different tracers. This is the same disk. This is, I think, TW Hydra. And this is a dust, large dust continuum emission. this is the molecular line emission, and this is the scattered light emission. And someone is always, yes, but these rings are corresponding to these rings. It's not the same scale. This emission is on the same scale of this, but this one is more compact. So we really have to use more than one tracer because the emission we are probing is different and is telling us different information of the object. We will have soon two new facilities, SKA, which is an interferometer that is probing centimeter emission. For us, it will be very hard. There is one work from John Lee that is basically telling us that we need 100 hours to detect substructures. Dan knows about this. But there will be also ELT. ELT would be great because we will have extreme resolution. The problem of ELT is that we are detecting total emission, but of small grains. So we're not seeing anymore the scattered light emission. We are probing the total flux, a lot of information, but that means that also substructures will be very hard to detect. We have to understand how to see them. There is also ERIS, which is a new instrument on the VLT that is probing basically the 4-5 micron regime that is giving us new information. The results are the work of a PhD student, so I'm very happy to advertise this work, Francesco Maio. He had a first survey of basically the fancy objects, and is also working on a couple of specific objects because they have some features that are thrilling. Everything you may want to test can create substructures. For example, Josh showed that also info can create substructures. So it's very difficult to understand what's doing what. So if you want my 2 cents, which are free to not trust, but I would trust this one. So we can divide the mechanisms into categories. The ones that are physically opening a hole, like you physically slow down the dust, you trap the dust is there for a while, planets, whatever. But there are also a lot of substructures that are generated like simply because your opacity is changing, you have a shadow. And this is not physically trapping the dust. So you're not creating a discontinuity between the inner part of the region and the outer part of the region with respect to the substructures. And those are basically the 2 different categories. I think they're both at play. I think Jeff has some work, for example, on these specific objects. But for us, if you're interested in detecting planets, we want to physically stop. We want to create a pressure maximum and slow down the dust there. And we're also interested in those pressure maxima because we want to form planets. We have a chicken egg problem here. We need the planets to form the substructures, or at least, you need something to create a pressure bump, and then you need to trap the dust, or at least accelerate the dust growth to form the planets. Because sadly, theory is, very jealous lover. And if you basically take the dust evolution and you try to understand what's a dust grain is doing in a protoplanetary disk, because dust is pressureless and gas is not, dust is drifting away. So if we don't understand how to form planets, our dust is going away on timescales that are faster than the one we have now we are now probing with ALMA. So we really need to slow down physically the dust. But could be that not all the dust traps are actually traps. Could be also some opacity issues. Okay, we need protoplanets that from now on for me will be simply balls with some gravity and capable to carve a hole. This is the exoplanetary population I showed you before. This is the planet mass versus distance from the star. Yay, we see out of planets. Nay, we don't see any planet similar to our solar system, which is pretty annoying because we want to understand how we are formed. This could be, observational bias. Hopefully will be populated soon. But then if you take all the images I showed you, the ones that are very pretty, and you put a ball in every hole, and you try to evaluate theoretically or more refinedly, in a more refined way with a machine learning approach, you evaluate the mass of those balls. This is the mass of the planets we are probing now. This is the mass of the planets we are detecting now. We know that there is also planet migration, but we have to understand also what's going on here. Are we not capable to probe those scales yet? Yes. Is there planet migration? Yes. But we really need to understand how to form those planets. And also I want to remember you that our planets are here. So we really also want to form planets here that we don't have here. So, we really have to understand a lot of things. And again, Maybe because I work too much with observational astronomers. For me to be really sure that it is a planet, you need to confirm the dot in more than one tracer. And this is very, very tricky. The only one that I honestly trust with all my life is PDS-70. And the only reason is because we have so many tracers in so many different instruments that makes a very robust detection. There are other ones. In my humble opinion, we are, all the sources that we are targeting in which there are candidates are probably candidate objects. I'm not sure we are detecting the protoplanets because protoplanets should emit H alpha and we don't see them. Maybe we see some envelope around them, but that means that we need to understand what's going on between the planet surface and what we observe to then understand for sure what we see. This is an object I think everyone worked on it, PDS-70. There is also one of my simulation. I will use it in the future to show you what I do. But for now, this is what we can do with Phantom, fancy images. We can do better than this. I showed basically all the videos that I did in 2020 when I was young, and I didn't know how to do fancy videos. And then I realized that I don't have with me all the Phantom dumps, so I cannot do any fancier movie than the one I did 5 years ago, but that's it. As I told you, I'm also interested in binaries. So first of all, because if you look at the occurrence of binaries in evolved stars, it's far larger than the one we are detecting. Secondly, because more than one star, more fun, a lot of disks. We can do a lot of chaos around those objects. So you have a lot of observational signature to test in your models. And again, we are observing both P-type and S-type planets, so we really need to form them. There is another reason why I'm interested in stars, and it's basically how I now define the objects I'm working with. Also, two stars are basically two balls embedded, capable to create holes. So a low mass star could be a high mass planet in my simulation, according to the primary mass of the star. Sorry, according to the star of the primary mass, because the physics is the same. And this is why, we really have to be careful once we divide binaries or, giant planets, because according to the mass of the primary star, the effect of a very massive planet is basically the same of a lower mass star on a higher mass primary. So this is why I started to work also on this. And I already told you, we know that they are there. We have to understand where they are. And this is basically what I did in the last 5 years, which I call see the invisible, which means we can use different mechanisms to indirectly spot where the planets are and then devise new observation to understand if the hypothesis is really correct. This is basically what people are using. So trace the position of the planet using the spiral, but again, the degeneracy here is huge. A lot of mechanisms can generate spirals. Use kinematic asymmetries to detect the position of the spiral of the planet. Again, the degeneracy is huge. There are a lot of mechanisms that can generate kinematically asymmetries. You would be very happy if you have a dot in the middle of nowhere of dust, because that could be a circumplanetary disk, so material around the planet. We have just one object here, and in my opinion, it's peculiar because there is a connection, is a spiral connecting the outer reservoir of dust and the accretor here. Because again, if you put some dust around an object and you evaluate how long the dust should be there, if it's pure radial drift, is very, very little time. If the object is creating a hot envelope, is even smaller timescale, because dust should be destroyed. So this is what a lot of people are doing. Take our physics that we want to test. We are using Phantom plus MC post. So from the physics we want to test, we extract a flux that we want to use to compare with observations, and then understand what we are doing. This is the framework that everyone is using. Our cool simulation, shown here in this beautiful picture, and this is our cool flux. And the reason why I did this image is because this is not one-to-one. It's mostly one-to-one, and not even one-to-one, if it's a bright dust emission with a very high resolution. You are still filtering out some scale, so be careful when we don't, so if you don't post-process correctly your flux, because you may keep some observation, some feature that is actually filtered out in the observation. But when you do, for example, scattered light images, the observation is very different from the model. So what am I doing with my life? Apart from convincing you that it's difficult to see perturbers in disk, I'm interested in basically objects that are hosting two giant planets or two giant perturbers. And the reason why I'm interested in giant stuff is because, again, maybe we can see them, while the lower mass planets are very, very difficult to detect. And secondly, because our solar system hosts two giant planets, they are not as giant as this one, but we know that there is a strong impact on the evolution of the system, and specifically they can disconnect the inner part of the disk with respect to the outer part of the disk, as in PDF70. So a thing that I really like of putting two double giants is that according to the different initial conditions, or final position, choose your word, of your simulation, you can have different morphologies, even if the scenario is the same. Two perturbers, very massive, in a protoplanetary disk. Specifically, you can carve a huge cavity, like in PDF70, or you can preserve a dust field between the two, like in the case of HD 169142. And this is basically the sources I modeled in the last years. Two rings, two planets, one ring, one planet, two rings, two planets. But what is interesting here is that, also the morphology of the two rings is different case by case. PDF70, bright ring, all inner disk. HD 169142, outer ring splitted, inner ring very bright, maybe something inside. This is HD 10546. If you go in there, a lot of papers are showing HD 10546 as this image, a very bright 20 AU ring. But this is because people are not looking in the archive, because actually this object is huge. There is a super faint outer ring at 200 AU detected in cycle 0, Catherine Walsh data, that people are not showing because the high resolution data cut out the larger scales. But actually this disk is huge. So basically, even if you have two planets here, here, and here, the properties are very different. Specifically, this ring with respect to this ring, the flux ratio is 1000, while this ring with respect to this ring, the flux ratio is less than 10. This is why I'm very interested in this kind of objects, because they really, really impact our protoplanetary disk. And this is basically what we do. We evolve our dust and our gas. We check what's happening. In this case, I'm preserving the dust ring. We select a snapshot that, in our opinion, is decent. Surface density, distance from the stars, position of the planet, cavity in the gas, preserve everything in the dust. And then we post-process with MCFOST, and we post-process then with CASA, because what we want to check is not the infinite resolution flux, is what you get from an observation. And ALMA is cutting the lower and the smaller and the larger scales efficiently, because this is how an interferometer works. And this is basically what we get. So this is how I propose that this hypothesis could be reasonable, at least one perturber here and one perturber here. This perturber here, I think Pedro modeled it with a binary, could be that is a massive object. It cannot be bright enough to be detected, because otherwise we should have seen it. But again, should be massive enough to open the cavity. That's the only constraint we have. There is another thing, I don't want to go into the details here, but one thing that you can do, you can also test different dust sizes, because we can have multi-grain observations. And what you can get, you can test your spectral index. And this is very important, for example, if you want then to do change instrument and, for example, go for JWST, because you want to have a very accurate modeling of your dust size distribution if you want to have observations on some other dust size that we don't probe, for example, with ALMA. And then this is what I was referring before. If you use your model to try to understand what's going on, so I connected this asymmetry with the spiral of an induced planet. I contacted them, then had a student, Jan Hammond. They went with Valentine Christen on the archive, and they basically found that there is a blob moving Keplerianly in the scattered light. Yay, we can see a planet. 9, this is not exactly the planet, because it's a scattered light emission, and planets are not emitting scattered light emission. So we are seeing some thing, clamp, moving Keplerianly, where there should be a planet, but maybe, it's a planetary envelope, or some material on top of the planet, but it's not exactly the planet. Another thing that we can do is predict the properties of some traces. For example, this was a prediction on the gas property. This is HD 10546. To carve a 100 AU gap could be everything, right? I mean, let's face reality, could be one planet, could be more than one planet, could be 50 planets. It's 100 AU. But what you can try to test is if you have at least one massive perturber, you should carve a gap in the gas. While if you have a system of lower mass perturbers, you're not carving the gap because the mass of the planet is smaller. And you may say, well, but PDS-70, you know, the cavity is huge. But PDS-70, the planets are at 30 AU. These are objects at 150 AU, 100 AU. Carving a gap where H over R is a decent value and you're far away in the planet requires a very massive planet. So we predicted this, and this is the observation of this object. And you see, clearly the cavity is carved in the gas. Whatever is doing this, planets, not planets, has to carve a cavity in a lot of traces, which means that the gas cavity is open here. And again, please remember to check all the scale of the disk. This is the inner part of this disk. This is this, and it's probing only this chemistry, this physics. But you see, in scattered light, if you go a larger scale, you see that there is a hole. So basically, this back disk here is this one. It's not this one. You could see that the cavity is open here because you see the back part of the disk in the smaller scale, and you see the other back part of the disk in the larger scale. So it's very important to study the system in all the tracers and to all the scale, because that gives you strong constraints on what you want to do. Then once you have a model that is matching something, you can have predictions of something else. For example, PDS-70, dust. You see the flux is decent, so I tried the gas. And for example, here we can see that I couldn't even empty the cavity enough because I was reaching the phantom lowest limit for my cavity. And then you can study something on the evolution of planets. But most importantly, again, you can predict something. I think that Josh is the only one who did something like this. So this is the flux in like micron size, but this is not what you observe with sphere, because sphere requires a heavy post-process. So this is the flux, and this is the ABI image of the flux. You lose a lot of feature, but then your image is far closer to the one observed. And again, you can use it also for prediction. For example, this is JWST, NIRCam, and this is the observation of the spiral. In the last 2 minutes, why binaries? I mean, the problem of binaries is that we don't see many of them, and even the one we see, we don't know them. This is GG tau. It's a nightmare. It's the brightest object, I think, in the sky of this kind. And still, look at how little we know about the orbits, the inclination of the binaries with respect to the disk, and you know how important it is to know how many stars you have in your system, because accretion rate changes. So this one has been studied since 2010 and 11. There are 2 possible orbits. I mean, the cavity size, who cares? It's a hole. But what's important, you know, is the constraining of how planets and binaries are forming and how much you are accreting, because that changes a lot the outcome of your simulation and of your real evolution. We included 20 years, and still we cannot break the degeneracy because we are too far away from the periastron. But we resolved that this star here is not a star, is another binary. And we had enough data to constrain the secondary orbits. So actually, this object is not a binary, it's a triple system. Actually, no, this object is not a triple system, it's a quintuplet. And every object I'm adding is adding complexity and physical mechanism. And this is why it's very important to know at least the easiest part, the orbits. There is another thing that is worrying, and Enrico already told this, is eccentricity. So you have the same simulation, this is the same simulation, this and this, 2 orbits, who cares? Larger cavity, yay. But the problem is that after a while, both simulations change aspect, because we have eccentricity growth in cavities due to the binary interacting with the disk. And that's a bit annoying because your model is matching or not matching in a timescale, and then matching or not matching in the other timescale. That makes me think that maybe we need to understand better, as Enrico is doing, what is happening when you have eccentricity in your system, and if thermodynamical effects, you know, a different prescription for the equation of state can impact the timescale for this growth. Also, because in the literature, I found 10 objects, 5 are circular and 5 are eccentric. So who knows? Finally, you can use your model, put your flux on the observation and check which is the best one. Fine, probably misaligned. We know there are perturbers. I hope I convinced you it's difficult to see them. Last minute. We are working on Mikado. As I told you, SKA has been probed. For example, John has a paper, and there is also Jesse Speedy and Yin-Hao Wu that are leading a chapter on a white paper for understanding how substructures could be observed with SKA. On Mikado Morpheo, we are working on it. Again, advertise of a very unknown person here in Grenoble, this unknown PhD student, Antoine Alaguero. And together we are doing models with MC Fost to then understand how ELT will detect substructures and exoplanets. We can see Jupiter planets in open gaps. Do we have candidates? Yes. In my opinion, something will be detected here. We will detect gaps, but we need bright stars, and that's a bit complicated. And this is my last slide. You can recycle your model to test how good it is on different wavelengths. For example, this is VLT, this is the sphere PCA observation. This is Eris, like my model treated with the pipeline of Eris. We could detect the planets and also the spiral. Spoiler, this is what people see. And this is what preliminary results of ELT will show. And because it's more or less on same scale, if you do a proper analysis, which means not plotting on different scale, you can also check if, for example, you are seeing different edges of the spiral. And this is super interesting because for people that is interested in understanding the spirals, maybe if we have a three-dimensional idea of the edges, we can understand maybe the mechanisms. And this is it.
Time for questions? I can start by lobbing one in. Just for discussion, I mean, these are quite massive planets that we're seeing. So they're like super Jupiter at least. So do you want to speculate about where they come from?
Okay, so yes, but this is speculation. So first of all, I want to say that when I was working in the planetarium, because I quitted science more than once, people asked me, could we detect gravitational waves? And my answer was absolutely no. They are too difficult to be detected. So that said, in my opinion, what's happening is that some of them, for example, HD 10546, if you have something big at 100 AU, could be fragmentation, right? Self-gravitating fragmentation. Fine, easy. When you have a PDS 70 system in which you have big boys close to the star, in my opinion, what can happen is that maybe you fragment the dust. So you create a core, fragmenting only the dust. Maybe the gas mass is not enough, to be this violent fragmenting system that we all imagine because of, previous results. You can fragment the dust, create a core, and then the core can rapidly accrete. What I think is interesting in PDS 70 is that according to all the models, the outer planet after a while should become larger in mass because the reservoir filters fine, but encounters before one planet and then the other one. B is basically probably accreting more. So you should form something very close before getting the other one. And this is what I honestly don't know. But again, self-gravity.
You mentioned while discussing rings and gaps that we had a chicken and egg problem to form planets, that we needed a planet to produce the gaps and the rings, and we needed the rings to pile up material and produce the planets. I'd like to offer a different view. Because of gas drag, no need for planets. Dust piles up in the mid-plane, and that's nothing else than a dust trap in the vertical direction. And when gas to dust ratio gets close to 1, then all sorts of things can happen. So you might not need a planet after all, to start with.
Yes, I agree with you. The problem is that we go back to the fact, yes, but then we are capable to test their presence only when they are massive enough to open something. which means that, it's very difficult. Even if you form let's say you form a core, you open maybe just a gap in the dust, or maybe not even that, it's not detectable for us. At the state of the art, I'm not sure we can probe this scenario because we don't know how to see if they are there, but for example, very, very limited in mass. How do you trust someone detecting a 20 Earth mass gap at 70
I'm not even talking about the gaps. I mean, there's a mid-plane layer that's optically thick and massive.
No, yeah, but how do you see them? If this is my problem is really it could be an option, but it's one of the untestable ones. How do I test that I have this mechanism at play?
There's at least observations of very thin dust disks that could pancake collapse.
Yeah. Oh yes, definitely.
A small comment on Francois' comment. The skeleton handholds on stick, so that picture can't go to the right. So settling as uniform against dust is hydrodynamic stick. So something else needs, I think something else, Zoom is missing. But yes,
but it's a fact. It's a fact that there's a massive dust concentration in the midplane, and some of the conditions are definitely present to make that streaming unstable, streaming instability.
But I am fine. Everything creates something that then is capable to open a cup. I'm happy because then we can see them.
So when you calculate those synthetic images with a planet inside the disk, what do you assume about the
like this?
Yes, something like that. About the emission from the planet, and also in phantom simulations, how do you treat the radiative transfer there?
So, two different questions. So the easy answer is that there are several ways you can use those sinks particles that you have in phantom. So usually what I do when I'm lazy, which means that I want to test my pipeline, I basically take the mass of the planet and then I use the Allard or SIS automatic MC-FOST track, and it's the natural luminosity of the object. But then if you want to do something more fine, for example, you want to test how different planetary fluxes can be detected, you can inject the flux manually forcing MC-FOST to have an object of that luminosity and that radius. Another thing that you may want to do is simply take where the position of the planet is, assume something analytically simple, create ad hoc objects, inject in the position, and then post-process your object. We did also this with Valentin when he was doing the JWST observation. That depends on you. So regarding the hydrogen,
just a comment. The reason I'm asking is because if you have a planet carving up a gap, it will accrete a lot of gas.
Yes.
So it's going to be quite considerable accretion luminosity. So maybe it's easier to see if you include that accretion.
Yeah, that's the thing. We can try different things, but I always prescribe it. Regarding thermodynamics, this is the simple local hydrothermal equilibrium. This is why one of the things I should do is a measure of the accurate, measure in more accurate way the temperature layer, not only for the dust, mostly for the upper layer, for the scattered light.
All right, I think we better leave it there. But let's thank Claudia again for an excellent talk.